Now see a AC circuit containing pure inductor only here. So in this case, we take here inductor like this, made of any conducting material, conducting wire, and AC source is applied over here. That suppose EMF at an instant is E, and its inductance, that is L here. Now what happens when the current is passed through this, as EMF is applied, EMF here external EMF is applied, and EMF is induced in the coil here, which opposes the increase of the EMF in the circuit here, and also the decrease of the EMF or decrease of the current in the circuit. So according to Lenz's law, whatever the EMF is induced, that is going to oppose increase or decrease of the current. So here in this case we can write E minus L di upon dt is equal to 0 according to Kirchhoff's law. So we can write here L di upon dt is equal to E, and we can write here di upon dt is equal to, in that case, E upon L. And now here we can write di is equal to E naught sin omega t upon L, that is dt. So by this equation now we can calculate the current. So we know the EMF here in this case, that is E is equal to E naught sin omega t. So EMF is applied at an instant is this, and now the current is not given here. So we have to calculate the current by using this relation. So now we integrate it. When we integrate this equation, we will be getting, in this case, I is this di is equal to E naught upon L is here constant, and here sin omega t dt. Now when we integrate this, we will be writing I is equal to E naught upon L. Integration of sin omega t can be written here minus cos omega t upon omega plus any constant k we write here. But now see here, this constant is here is the actually has the same dimension as that of current, and it is here time independent here. But we in this equation here see EMF is varying here, or that you can say oscillating symmetrically about the 0. Similarly, current is also oscillating symmetrically about the 0. So there is no such constant which is actually time independent. So this constant, or the value of constants, is taken 0 in this case. So you will be writing I is equal to E naught upon omega L, that is cos omega t. That can be written I is equal to E naught upon omega L can be written here I naught. So we can write minus I naught, and here cos omega t can be written here sin pi by 2 minus omega t, that is 90 minus theta. So we can also write I is equal to I naught sin omega t minus pi upon 2, this negative sign we have taken inside here. So and already we have done E is equal to E naught sin omega t. So if we look at these two equations, EMF and the value of the current in the inductor, we will see here the current is lagging behind by a phase of pi upon 2. So there is a phase lag between the potential difference or the EMF applied and current, and that is of the pi upon 2 here. So this is about the current and EMF in the inductor only, that is which is the pure inductor actually. Now we can also calculate here, we can just define this thing is here. We just wrote I naught, you know here I naught is equal to, actually I have taken E naught upon omega L. Omega L can be given here, this is the resistance XL, and this resistance is offered by inductor due to induction of the EMF. So that is called here inductive reactance. So XL is known as, actually here XL is called inductive reactance. Its unit is also omega, but XL is equal to, we write here omega L, that is 2 pi nu L, and nu is the frequency of the AC applied here. So XL is actually depend on the frequency. When you draw its graph, you will be getting XL and nu, the graph is like this, straight line. From here it is very much clear here. But if you have taken the steady value of current or the direct current, that we can write here for DC, you will be getting XL is equal to 0 because nu is equal to 0. So if the current does not vary and it has no frequency, or that is a direct current or a steady value of current, then the inductive reactance is 0 for that. So, this is the about induction and the inductor circuit. Let us discuss the graphical relation between the EMF I and the phasor diagram for the inductive circuit. Now, say if you know the relation, mathematical relation between them. Suppose you have taken EMF and I both this side here and this is time. So, for the EMF graph is suppose like this, this is the peak value of EMF. Then the current graph can be taken for the current, since the current is lagging behind in inductor. So, we can write it is here like this. This is about the current. So, this is showing here the instantaneous value of the current here. Current is lagging behind the voltage by pi by 2 here. So, this is starting from the negative side, and its phasor diagram can be drawn this side here. Suppose this here x and y you are taking, this is the origin. EMF is this side, E naught, that is omega t. So, current will be somewhere here, and this angle is called here pi upon 2, and this is here I naught. So, current is lagging behind by an angle of the pi by 2 here. So, this is the phasor diagram for the current and voltage in the inductive circuit, and this is the graphical relation or the sine curve for the EMF and current in the inductive circuit.